Good evening mga lagan. So we will continue with answering this assignment. We got this one the other day, and this time we will be solving a deflection of a beam. So the problem is determine the maximum deflection of the beam shown by double integration method. Use modulus of elasticity equals to 200 gigapascal and the moment of inertia I equal to 400 times 10 to the sixth millimeter to the fourth. So first, we will get the reaction. So in order to um, get the moment equation, we have to solve for the reaction. So say this is point A, and then this is point B. So we have RA and then RB on the left. So first, we will try solving the reaction at A. So we will say summation of moments at this location at point B. So summation of moments at B is equal to the moment at B. But since this like the point B is a roller support, so there is no moment. So we can say summation of moment at B is equal to the moment at B, which is 0. So summation of moments at B is equal to 0. Therefore, RA is equal to the concentrated load 30 times 7 and then plus the uniform load, which is 20 times 4, and then the moment arm is, this is total 11 minus 2, this is 9, and then divided by the moment arm or the span, which is 10. So the reaction at A is 30 times 7 plus 20 times 4 times 9. Wait. So 30 times 7 plus 20 times 4 times 9 divided by 10. So this is 93 unit kilonewton. So that is 93 kilonewton. That is the reaction at point B or point A. So RA, reaction at A. So this is RA. Now, we will also calculate for the reaction at B. Now, summation of moments at A. So, to get the reaction at B, we will sum up moment at point A. So, summation of moments at A is equal to the moment at A. Now, the moment at A, because we have the cantilever, that is not equal to 0. So, first, actually we have two solutions here. It's either we will equate the equation summation of moments at A equal to the moment of A, and then just cut a section or a segment, consider a segment, or you will use the total load and then equate the summation of moments at A equal to 0. So first we will do the first solution, which is summation of moment at A is equal to the moment at A. Now, if you look at the load diagram, we have uniform load. We have a cantilever which is 1 meter. So we will draw the load diagram. So this is 1 meter, and then this is, if we cut section from the load diagram, if we cut section here, this one, and consider left of A, reaction A. So this one, this is our free body diagram. So this is our load, which is 20, then the cantilever is 1 meter. And then this one, this is not the reaction A, but the shear at A. And then since our load is counterclockwise, therefore our moment at A is equal to counter or clockwise. No? So the load is counterclockwise, so the moment at A. So this is our moment at A. So therefore, moment at A, summation of moments at A is equal to the moment at A. So moment at A is equal to 20 times 1 times zero point 0.5, which is 10 kilonewton meter. Now, with this moment at A, we can solve for the reaction at B, and then we sum up moments at A. Right? So again, we will consider we will cut section and consider right of A. So now this time we will consider right of A only. Oh. So this is our uniform load, and then this is 20 kilonewton meter, but this time this is only one, or was it 1 or 3 meters? So sorry. So that is 3 meters, the moment arm, or the distance of the uniform load, and then we have a concentrated load of 30 kilonewton, and then this is 7 meters, and then this time this is the shear at A to the right of A, or shear like to the right of A, and then now our moment, so we have moment here clockwise. So when we consider the other side, it will now be, so this is our moment at A, which is equal to 10 kilonewton meter. And then we have our reaction at A going up, oh no, RB, reaction at B, and then therefore summation of moments at A is equal to the moment at A is equal to 0, or no, 10. So if you look at this diagram, our moment at A is clockwise, right? Or counterclockwise, the reaction at B is counterclockwise. Therefore, MA, which is 10 plus RB times 10 is equal to the clockwise, which is 20 times 3 times 1.5. Will it fit? We'll put it in below. That one. And then this is plus 30 times 3, right? So therefore, RB is equal to 20 times 3 times 1.5 plus 30 times 3, and then minus 10 transpose the moment at A, and then divided by RB. No, divided by 10. So this is 17 kilonewton. So to check, RB is 17, RA is 93. So RA 93. So therefore, the total load is 93 plus 17, which is equal to 200 or 110. So this is, yeah, 110 kilonewton. Now, if you look at the load diagram, so 30, we have concentrated load of 30 kilonewton, and then 20 times 4 is 80. So 80 plus 30 is 110. So therefore, our reaction is correct. Now, the other solution is, if you consider the whole load, you can instead of cutting section and then solve for the moment of A, you can actually assume summation of moments at A is equal to 0, and then consider the whole load. So therefore, if we go back to our diagram, so we have cantilever here, and then this one, and then concentrated load, which is 30. So this is 20. This is RB, right? This is RA, and then this is 1 meter, 3 meters, 7 meters. So what you can do on this one is summation of moments at A, and then consider the total load. So therefore, RB going clockwise direction is equal to 30 times 3, and then plus 20 times 4. Now, this time, our moment arm, our resultant for this one is right here at the middle, which is 2 meters from the free end, and then from the point A, that is only 1 meter. So this is 1, and then divided by 10, like that. So submit this 30 times 3 plus 20 times 4, then divided by 10 is 17 kilonewton. So that is the same. So it's either you cut section here and then get the moment at A, then summation of moments at A is equal to the moment of A, or you could just directly assume, consider the total load and then summation of moments at A is equal to 0, then um, get the reaction at B, right? Or what you can do is, since you already have reaction at A, you can sum up moments at the free end. Because you already have reaction at A, which is 93 kilonewton. So we will try solving that reaction at B using summation of moments right here. Now this is the free end. This is cantilever. So summation of moments at A, the moment at this location is 0. That is the start of the load. So the other solution, or the third solution, is summation of moments at this, shall we say this is C. So summation of moments at C is equal to 0. So therefore RB, right? RB times the total is 11, and then plus RA times 1, and then is equal to counterclock or clockwise is 30 times, now the distance of the 30 concentrated load is from here is 1 plus 3, which is 4, and then the uniform load plus 20 times 4, and then the moment arm is, the resultant again is at the middle of the load, and then from point C, that is equal to 2. So we will solve this one. Therefore RB is equal to 30 plus this one, and then minus, so we will just simplify this one. 30 times 4, or rearrange. Then this is plus 20 times 4 times 2, and then minus, transpose the RA, which is 93 times 1, and then divided by what? 11. So we will see this is 30 times 4 plus 20 times 4 times 2 minus 93 is equal to, divided by 11. This is 17. So regardless of what's your procedure, what option you want to use for calculating the reaction, it should yield the same answer as long as your solution is correct. You assume, say, whichever you like, say summation of moments at point C, and then consider the total load, considering reaction at A as well, or you will cut section at reaction at point A, and then to get the moment of A, just consider the left side because there is no other unknown, and then to get the reaction at B, then cut another section, then consider the right of A. Or consider the whole load, summation of moments at A is equal to 0. So that's the same. So as long as it yields the same answer, then it should be fine, right? So I think at the university or at the school, the most common solution that were taught was to calculate the summation of moments at A equal to 0, considering the total load is 1. Even at the when I was still at the university, this is the solution that was taught by us or by our professor to us. This one. But if you understand the theory behind this one, like how to get the reactions or how, like, I think in strength of materials, you are taught to, for example, you calculate the um, forces of a thrust. Remember, you were taught to, like, you have two solutions. First is using a method of joints, and then the second solution is methods of section. So this is the same. So this solution here, the first one that I did, this one, this is called this one. This is the moment or the methods of section. You cut section as long as you draw the correct free body diagram. So that should be fine. So we have reaction at A equal to 93 kilonewton, then reaction at B equal to 17 kilonewton. So to get the moment, let's have another page. So going back to the problem, now, so we already have the reaction at A, which is 93, then reaction at B is 17. Now, the summation of, or the formula for the deflection calculation using double integration, so that's why it's called double integration, because the moment equation is equal to the second derivative of your um like moment, or the moment equation. So we have this. So the second derivative of y is equal. It's equal to your moment over ei. So this is our general equation. Now ei, since this one, since this moment of inertia and or modulus of elasticity and the moment of inertia is constant the entire span, so we can transpose this one, disregard that one first, and then our equation would be ei, and then second derivative will just use double prime, y double prime is equal to your moment. So since this is constant, I mean there are times that if the modulus of elasticity or the flexural rigidity, this term ei, is not constant, then you will include that in the equation. But I've never like, even when I was still a student in the university, I've never seen a problem with different flexural rigidity. So I don't know. So on this one, the modulus of elasticity and the moment of inertia is constant. So we can just for now we can just disregard this constant. Then we will just apply that when we uh, finally calculate for the deflection. Now to get the moment of the deflection using the double integration method, the first assumption is the load is continuous, right? So, and then you will cut section that would cover um all of the load. You can do like by segment, like from, if this is point C to A, and then C to, if this is point D, C to D, that's fine. But if you want to get the general equation of the entire beam, considering the entire load, you have to consider um cutting section that would include all of the load. Now, since this is um, not a it's a uniform load, but not the entire span, then what you will do is you will extend this load, this one. So which is the same, 20 kilonewton. Now, since you add a portion of a uniform load at the top of your beam, to counter that one, you have to add also the same load, the same quantity, the same length, but going up. So it is as if you add, say, a 500 kilonewton going down, and then um apply also 500 kilonewton going up, so that would cancel out. So this is the same as just the original load. But the reason why we have this one is to have a continuity of your um loading, and then consider a location where you will cut your point X, with the moment there, and then that would include all of the load. So we cut section here. Now this is our X, and then free body diagram again. So summation of moment at X, this is your distance X, is equal to the moment at X, right? And then that already includes your reaction, um, the uniform load, and the concentrated load. So we will express this entire loading in terms of X. So first, right? So moment at X is equal to, so moment at X is equal to, so if you cut the free body diagram, so you have your shear at X here, and then moment at X. So moment at X is equal to, it's assumed what we call this one, going, it doesn't matter if you assume if the moment at X is going up or clockwise or counterclockwise or going clockwise, it doesn't matter, because once we solve the deflection, the sign configuration of the deflection will determine if the deflection is going down or going up. So that's fine. So moment at X is equal to reaction at A, which is 93. Oh no, since our what's it? Possible. No, we will just most likely our moment at X is counterclockwise. So we will just assume that our moment at X is counterclockwise. There's a bigger chance considering the diagram, the load diagram. So moment at X, that is clockwise. So moment at X is equal to your RA, which is 93, and then your moment arm is, if this total distance from the free end to the point X is X, then your moment arm is X minus 1, right? So that's your clockwise movement. Now, your load is counterclockwise, so we will use minus. So minus 30 times, again, x minus 4. And then your uniform load is minus 20 times your length is 4. And then your moment arm. So again, our resultant here is at the middle, which is 2. So therefore, this is x minus 2. Oh, no, not 4. Not 4. Because we already extended that load. So 20 times x, right? Because this is the total load, uniform. That's already the entire span. So 20 times x, and then times x over 2. And then we have another counter. or clockwise, which is your load upward, this is plus. No, this is the same sign as your reaction, the same direction, clockwise. So this is what? This is 20 times um, x minus 4, and then times x minus 4 over 2. So this is x squared over 2. So this is our general equation of moment at x. No? So this is the first, this is the reaction, this one going clockwise, and then the load at the bottom, which is also clockwise, this one, 20 times x minus 4, then x minus 4 over 2. So this is x squared over 2. Or we'll just, this one here. So x minus 4 over 2, that one. So it's clear. And then our clockwise direction, the same direction as your moment at x, and then since this is opposite side, then it would be negative. So minus 30 times the reaction, or the moment arm is 4, or x minus 4, and then the uniform load, which is 20x times x over 2. And then we will simplify this one. So mx is equal to 93 times x minus 1 minus 30 times x minus 4. And then this one minus 20, no, minus 20 over 2 is 10 x squared. And then this one plus 20 over 2 is 10 times x minus 4 squared. So that is our moment equation, right? So this is equal to, this is, since our mx is equal to the second derivative of your deflection, therefore y, second derivative of y is equal to the same, 93 minus x minus 1, or times x minus 1 times 30 times x minus 4 minus 10x squared plus 10x minus 4 squared. So that is our equation for the second derivative of your deflection. Now, first we will integrate this equation. So integral of y, like second derivative of y, is y prime. Now the first integration of your moment is equal to your slope. So second derivative of y, so second derivative of y, this is equal to your moment, and then when you integrate that one, dy over dx, this is your slope, and then of course integrate that again, so that is y, and that would be your deflection. So second derivative is moment, first derivative is slope, and then the y is equal to your deflection. So we will first integrate this equation, this one, right? So if we have, say, integral of x to, oh, so if we have integral of x to the n dx, the integral of that one is x n plus 1 over n plus 1. So using this formula, we will integrate each expression or each equation here, each part of the equation, using this formula here. So 93 x minus 1, x minus 1 without exponent, so it means this is 1. So that would become, our x is 93, or no, our x is x minus 1, and then this is constant 93, so that would stay the same. So that is, so y prime is equal to 93 constant, then x minus 1 squared over x n plus 1, which is 2. And then this is the integral of 30x minus 4 is equal to minus, oh, minus 30 times x minus 4 squared over 2. And then minus, what's next? Minus 10x squared. So that would become minus 10x cubed over 3. And then the last term would be 10x minus 4 squared. So 10, is it plus? Yeah, plus. So plus 10x minus 4 squared. So this is now cubed over 3. So 93x minus 1 squared. I will just sum this out first. So 93x1 squared over 2, then 30x minus 4 squared over 2. 10x squared would become 10x cubed over 3. Then 10 times x minus 4 squared will become cube over 3. So this is our equation. And then we will add our first constant, which is C1. Now, integrating this again, that would give us the final equation for our deflection. So 93, the same formula from this formula here, right? So using that same integration formula, so y squared or y is equal to 93 again, and then x minus 1 squared will become x minus 1 cubed, and then we have the original 2, then times 3, which is the n plus 1, so that is 3, and then minus 30 over 2, this is now 15, and then x minus 4 squared will now become x minus 4 cubed, then over 3, and then minus 10 x x cubed will become x to the 4th, and then this is this is 3 times 4, right? So 3 times 4, this will become 12, or we will just so this is the original 3, and then times 4. 4 again is the 3 plus 1, and then on this one here is 10 times x minus 4 cube will now become 4, and then 3 times 4, it won't fit now, and then plus integral of constant is C1 x, and then your another constant, your second constant, C2. Now this is our final equation for the deflection, but we have first to solve the values of C1 and C2. Now going back to our deflection or the load diagram, this one here, we'll just add another page. Y is equal to, transfer our equation here, xy x minus 1 cube over 2 times 3 is 6, and then minus 5 times x minus 4 cube, and then minus 10x to the 4th over 12, and then minus 10 times x minus 4. Oh, x minus, what's that, 4? 4 over 12. So that x minus 4. Yeah, and then c1x plus c1x plus c2. So that is our general equation. So first, we will say at x is equal to 1, right here, at point A, the reaction or the deflection is 0 because that is at the support. So we can say at x is equal to 1, our deflection is 0. Then solve for C1 and C2. That is our first equation. This will be as two equations to unknowns because we cannot have a if this is if there is no cantilever, this would be easier to solve for the constant C1 and C2. So we will substitute first what is the value of y if x is equal, or no, in this equation, substitute the value of x, which is 1, and then get the first equation for the C1x or C1 plus C2. So at x is 1, so this will become x is equal to 1, x minus, or 1 minus 1 is 0, so this will become 0. Our first term would be 0, and then minus 5 times x minus 4 cubed. So now in calculating for this one, if this term here, if this term will yield a negative value, say for example x is 1, 1 minus 4 is minus 3. So if it yields a negative number, you will disregard that in the calculation. So you can directly say that this term here is 0. And then minus 10 times 1 over 12. And then minus this one again, x minus 4 will yield a negative value. So this is 0. And then plus C1x, C1 times 1, and then plus C2. So, and then the total equation will 0 because this y is equal to 0. So we have our first equation C1 plus C2 is equal to, this is negative, transpose, this will become 10 over 12 or 5 over 6, right? So this is 5 over 6. So that is our first equation. Now the second equation will be if x is equal to at point B, your deflection is also 0 because that is a support. So therefore, our second condition is at x is equal to the total length, which is 11, y is equal to 0, and then solve for C1 and C2. So we will substitute y is equal to 90. Now this time our term x minus 1 will yield a positive value, then we will consider everything. If this is only minus 4, then this one here, this one is also minus 4. So 93 x minus 1. So this is 93 times x minus 1 is 10, then cube over 6 over 6, and then minus, we have 5 x minus 4 is 11 minus 4 is 7. So this is 5 times 7 to the fourth, and then minus 10x, no, minus 10x to the fourth over 12. So this is minus 10 times 11 to the fourth over 12. And then plus or minus. Minus, we'll just zoom this first. So minus, so this is minus 10 times x minus 4 is 7 to the fourth over 12, right? Then plus C1 11 plus C2. So that one. So simplify that one. So this is the total of this one is equal to 0 because that is our condition where x is equal to 11, y is equal to 0. So therefore, simplifying this one would be, so 93 times 10 cube divided by 93 times 10 cube divided by 6. So this is 15,500 minus 5 times 7 to the fourth is 12,005, and this one is 10 times 11 to the fourth divided by 12 is 12,200.8333, and then this one is 10 times 7 to the fourth divided by 12 is 2,000.8333, and then plus 11 C1 plus C2 is equal to 0. So this one will simplify this one. 15,500 minus 12,005 minus 12,200.8333 minus 2,000.8333. So that is 10,000. So this is minus 10,706.666 plus 11 C1 plus C2 is equal to 0. Now, we will first solve, or again, this is 11 C1 plus C2 is equal to minus 10,706.6666. Now, this is our equation 2. But we have our equation 1, which is C1 plus C2 is equal to 5 over 6. So therefore, C2, or we will eliminate C2, so we will subtract. So 11 C1 minus C1 is 10 C1. This one minus 10,706 minus 5 over 6. So that is minus 10.707.49993. Therefore, C1 is equal to 1,070.75. And then C2 is equal to, from here, is 5 over 6 minus C1, which is this is negative, minus minus 1070.75, right? C2 is equal to 1071, positive to 1071.58. So going back to our general equation, which is, which one here? So we can substitute this one here, C1x, Um, we'll just rewrite this one again. So 93x minus 1. So y is equal to 93 times x minus 1 cube over 6. Then minus 5 times x minus 4. This is to the 4th, right? And then minus 10x to the 5x minus 4 cube. This is not to the 4th. So this is cube, and then minus 10 times x minus 4 to the 4th over 12. Oh, 10x to the 4th minus 12 first. And I will just, that's fine. We'll just write. This is minus 10 times x minus 4 to the 4th.
Correction, the fourth term is minus 10
This
x to
one
the
should be the
fourth.
first, but that's fine. That's the same. And then plus C1x. C1 is how much? Minus 1070.75. So this is minus 1070.75 x, and then plus the C2, which is 1071.58. So this is now our final equation for the deflection, right? So the question is, determine the maximum deflection of the beam. Now, with this thing here, with the uniform load, not continuous, and then you have a concentrated load also, which is not in the midspan, we don't know the location of the maximum moment. So we have to first solve where is the location of the maximum, or not maximum moment, maximum deflection, or no, we will get first the location of the possible change in slope. So maximum deflection, if this is your elastic curve, say, so if this is your beam here, and then you have a support right here. So the elastic curve of the beam, this is exaggerated deflection. Now there is a point within this span where um your slope is basically from going down until it will go back like in the upward direction. So at that change in slope, where your slope theta is 0 of your elastic curve, that would correspond to your maximum deflection. So your maximum deflection is located where your slope change from going down to going up. So that is your location of your maximum deflection. Now we have to find the distance x where the theta is 0. Now if you remember, the first derivative of the moment is your slope. So going back to the first, which one here? This one. So going back to this equation, this is your slope. Now, once we solve for the distance x, we can solve for the maximum deflection. Now, using this equation, where our C1 is, um, where our C1, where our C1 is equal to, minus, how much was that? C1 is minus 1070.75. Minus 1070.75. Oh. 1070.75. So this is our C1. We will substitute it here and then calculate for the value of x. So remember, this is our slope equation. So again, at zero slope of your elastic curve, that corresponds to your maximum deflection. So 93x squared. So we will simplify this one. Um, so 93x. Now, without on this one, this is a cubic equation. You can, if your calculator can simplify a cubic equation, then you can use calculator. But before, my calculator when I was still at the university was Casio FX 350, because that's the cheapest calculator, scientific calculator at that time. So I even bought that from a pawn shop. So 93 x minus 1. So this is what we did before was just do trial and error. And then say x is, so let's say at x is 2. And then determine the value of slope. And then if it's negative, then you move to the right. Say, okay, at x is 2 point, or x at 3. Now, if at x is 3, this at x is equal to 3, the slope is positive. So you know from there that your location of your maximum moment is between 2 and 3. And then you'll just to keep trial and error until you get the closest possible location of x. It will not be a 0, 0, right? It will be like really close. So you can calculate for, since this is in millimeter or in meter, and then deflection is usually calculated in millimeter. So you can set your distance at, say, at the 0.001, right? Your assumption. So it will take time to do trial and error, but that's the easiest solution if it yields a cubic equation. So this one, 93x. So we will simplify its term first, so it's easy. So this one, 93x, we will simplify this one first. So 93 over 2 would be 46, 46.5, and then times x minus 1 squared is times x squared minus 2x plus 1. So that is our first term. So distribute. So this is 46.5 x squared minus 93x and then plus 46.5. So this is our first term. Now our second term is 30 over 2 is 15. So this is term 1, this is second term. So this is 15, 15, and then x minus 4 is, or x minus 4 squared is, this is times x squared minus 4 is minus 8x plus 16, right? And then, so simplify that one again. So this will become 15x squared, 15x minus 4. Yeah. So 15x squared, then 15 times 8 is 120. So this is minus 120x. And then 15 times 16 is 240. So this is our term or second term. And then our third term is 10x to the fourth. Oh, no, not that one. 10x cubed over 3. So our third term is 10x cubed over 3. So this is our third term. So this is 3.5 33x cubed, right? And then our fourth term is 10x minus 4 cubed over 3. So x cubed over 3, from this one, 10x cubed over 3, 10 over 3, then x minus 4 cubed. So this one is the same as 10, 3, and then x minus 4, and then x minus 4 squared, which is x squared minus 8x plus 16. And then distribute that one, 10 over 3 times x, right? X times x squared is x cubed. And then x times minus 8x is minus 8x squared. And then plus 16x. And then the minus 4 is minus 4x squared minus negative 4 times negative 8x is plus 32x. Then minus 4 times 16 is 64. Yeah. So this is minus 64. Then simplify this one. Combined common terms. So this is 10 over 3. So this is x cubed. And then x squared. This is minus 8x squared minus 4x squared is minus 12x squared. Then 16x plus 32x is plus 48x. And then minus 64. So this is our fourth term. So if we add everything, will it fit? Yeah. So adding everything here, this one, uh, that one there. We'll simplify this one first. So 10x cubed is 3.33x cubed. And then 10 times 12 over 3, that is minus 40x squared, right? And then 48 over 3 times 10 is plus 160x. And then 64 over 3 times 10 is minus 213.33. So that is our equation 4. So if we add all of this, so we have 3.33x cubed, and then we have 3.33x cubed. So that would give us y is equal to 6.667x cubed, and then x squared. So x squared, we have 40, and then we have 15. So that means 40 minus 15 is 25, right? So 46.5 plus 15 minus 40. This is plus 21.5 plus 21.5 x squared. And then our x, we have minus 93x, minus 93. And then we have minus 120 for the second term. And then the fourth term is plus 160x. So this is minus 53x, and then minus 213.333. So this is our this is not y prime. This is not y. This is y prime because this is our slope. That one. So we will solve for the value of x. Now again, if you don't have a scientific calculator that can um, solve a cubic equation. Now what I have here is this one. If x115 ES, so this is the same calculator I used when I took the licensure exam in May 2002. So this is already what, 21 years old calculator. So I'm still working. So simplify this one, which is 6. So we will simplify this one using a calculator. 5 equation, then 4 per cubic. A is 6.667, and then B is 21.5, then C is minus 53, then D is 213.33, no, minus that one. So our first, so there will be three value for x. So there you will have x1, x2, because this is a cubic equation, we have three value of x. So x1, x2, x3. Now using the calculator again, like I said, so first value x1 is 2.9954 meter. And then the next one is x2 is minus 3.11. This is imaginary number plus 1.005 I. So this is imaginary number. You can and then x2 is minus 3.11, then minus 1.005 I. So this x1 and x3, or x2 and x3 are both imaginary number. This one we have this I. So therefore our solution, or our distance x that corresponds to the maximum deflection, is at 2.999 meters. So if we substitute this value, right? If we substitute this value to the equation, this will give us this one right here. If we substitute from this general equation, our deflection equation, we will substitute x with 2.9954. So 2.9954, again, this term here would yield a negative value because that is x minus 4. So 2.99, so 2.99 minus 4 is negative, so that is 0. And then this one here again also 2.9954 minus 4 is negative value, then this is 0. So our final um, equation where we can solve for the maximum deflection is at 2.9954x, so that would become 93. So y is, or y is equal to 93 times x minus 1 cube over 6. And then like I said, the term with that it would yield a negative value, will disregard that one. So the next term would be minus 10x fourth over 12 minus 10x to the fourth over 12. And then the next one would be C1x. So C1x, so C1 is how much? 1070.75. So minus 1070.75, and then times x, and then plus C2 is, how much is C2? C2 is 1071.58 plus 1071.58. So therefore at x equal to 2 point, this one 2.9954. So 93, or we will just write the, so y 93 divided by 6 times 2.9954 minus 1 cube. This is 123.1464, and then 10 times 2.9954 to the fourth over 12. This is minus 67.0869, then minus 1070.75 times 2 point, or yeah, minus 1070.75 times 2.9954. This is minus 3207.32, then plus 1071.51. So therefore y is equal to 123.1464 minus 67.0869 minus 3207.32 plus 1071.51. So our deflection is minus 2079.7505. Now this is negative, which means our deflection is going down. Now the unit of this one, if you look at this one here, our load is in kilonewton. The reaction, this is the biggest term here, or the reaction 93. This is in kilonewton, and then the distance is in like cube. So therefore, our unit here is kilonewton meter cube. But this one, this is in terms of reflexural rigidity, EI. So we will now solve. Now our E is 200 gigapascal. Convert that to megapascal is times 1000. So that is 200,000 megapascal. Megapascal is the same as Newton per millimeter squared. And then I is, what's that, 400 times 10 to the 6 millimeter to the fourth. Now, since our equation is in Newton and millimeter, we will simplify this one into in Newton millimeter unit also. So kilonewton to Newton is times 1000 Newton over 1 kilonewton. And then the meter is 1000 millimeter over 1 meter. And then cube. So therefore, our deflection unit here for deflection is equal to minus 279.7505 times 1000 and times 1000 cube. This is 2.07975. This is times 10 to the 15. So that is, this is now in Newton millimeter, then divided by EI. So therefore, our Y, no, not bird Y. Our Y is equal to negative. So this is divided by 2000 or 200,000. times 400 exponent 6. 400. Yeah, 400. 400 exponent 6. Yeah. So again, also 79.7525 times 1000 times 1000 cube and divided by 200,000 times 400 exponent 6. So this is 25.997 millimeter. So this is our deflection, and then the distance is at x is equal to 2.9954 meters from the free end. So that is our solution using double integration. So since we have no, like, the question that was sent, there were no choices. We cannot we cannot compare this one with the choices, and assuming we got the C1 and C2 values correct. The procedure, that's the procedure. Um, the only way to check this one is if we have the choices for the answer, because I don't know if sometimes we do mistakes in calculating for the C1 and the C2, but the procedure is that's the correct procedure. So assuming our C1 and C2 is correct, then this is our answer. So deflection is 25.997 millimeter at x is equal to 2.9954 meters from the free end. So I hope this is clear, and see you on the next video.